And thanks everyone for joining today's seminar on fixed and random effects. I'm Jo Jacobs. I'm a health economist at the Health Economics Resource Center at the Palo Alto VA. And also joining me today is Laura Graham, also from HERC, and she'll be moderating questions and letting us know during the question period if there are any questions that come up. Also, a quick shout out to Liam Rose, also from HERC, who helped with some of the slides for this lecture. So before jumping into things, I'm going to note that these terms sometimes generate a lot of confusion because they can be used differently across different disciplines. So in economics versus biostatistics, for instance. Today, we're approaching the topic from an econometric standpoint. But at the end, we're also going to note how the terminology can be applied quite differently depending on where you look. So we're going to start with a brief poll, just asking everyone how familiar you are with fixed effects and random effects models.
So the choices that we have today are very familiar, B, somewhat familiar, C, not familiar at all. And the responses are coming in rather quickly. I'll give it just a few more seconds and then I'll close the poll. Okay, I'm going to go ahead and close the poll. And today we have A, very familiar, we have 13%, B, somewhat familiar, 68%. C, not familiar at all is 15%. And back to you.
Great. Okay, so we have a range here, a lot of people in the middle. Hopefully for those that are new to the topic, this will be an introduction to some new tools. And for those of you who are more experienced or somewhat experienced, hopefully it will provide either some new resources that maybe approach the topic from a different perspective. Okay, so since we're approaching the topic from an econometric standpoint, we're going to start today's seminar off with a brief overview of panel data, which is one type of data that fixed effects and random effects models can be used with. We'll also go over the panel linear regression model and use it to understand one type of omitted variable bias called unobserved heterogeneity. That can be addressed using fixed effects and random effects models. We'll then go over the fixed effects and random effects models themselves and talk about how we might choose between the two models. And finally, we'll conclude with some notes about differences in the use of terminology across disciplines. Okay. So I'll start with a brief overview of panel data. So that's, like we noted, one type of data that we use with fixed effects and random effects models. Panel data is the pooling of observations for the same cross-section of individuals or households, countries, firms, whatever the unit of analysis is, over several time periods. So in this case, we have data at the person level, and we observe each person over 3 time periods. Some of the factors, like age and income, you'll notice are changing over time. Other factors, in this case, sex and education, are not. So I'm also going to note here, and we'll touch on this again later, that the models we're going to explore in the remainder of the seminar can also be applied to cluster data, where instead of following a unit of analysis over time, we have observations that are clustered into groups. Okay, so if you attended our previous lecture on instrumental variables, you might recall that we provided an overview of the linear regression model. And you may also recall the model at the top of this slide, which is basically expresses how we predict how a unit change in X leads to a change in the outcome variable Y. This time, because we're dealing with a time dimension to our data, you'll note that we have an additional subscript T. So now we have YIT, which is the outcome for individual I at time T, xit, which is the explanatory variable of interest for individual I at time t, and epsilon it, which is the error term for individual I at time t. And you might recall that epsilon it contains all other factors besides x that determine the value of y. And one more thing you might recall, hopefully, is as Craig noted in her lecture, in order for beta hat to be unbiased and an unbiased estimate of the causal effect of x on y, x has to be exogenous. And we're going to recap what that means. Basically, what this means is that xit and epsilon it cannot be correlated with one another. So the explanatory variables in your model cannot be correlated with the error term. And Craig noted in her lecture on instrumental variables that there were instances where the error term will be correlated with the covariates in your model. And one such case relates to omitted variable bias. So if you're unable to include explanatory variables in your model, and these omitted variables are correlated with the explanatory variables in your model, then you will have biased predicted values of beta. Say, for instance, you want to look at the effect of education on income. And as in our sample panel that we showed a few slides ago, we can control for age, sex, and education. But we don't have data on things like innate ability or ambition. And since these things may be correlated with education, omitting these factors will lead to bias in our model. So today we'll talk about a special form of omitted variable bias called unobserved heterogeneity, and how some panel data techniques can be used to address this type of bias in a regression. Unobserved heterogeneity refers to omitted factors that may vary across individuals, but that remain constant over time. So, for example, at the individual level, this may include some demographics like race, ethnicity, family history, and maybe over the short term, innate abilities. At the state level, for instance, this may be things like geography, or over the short term at least, demographic, educational, or religious composition. So working with the equation we previously outlined for a panel linear regression model, we might think of this unobserved heterogeneity by breaking apart our error term, epsilon it, into two components. First, a component, UIT, and that varies over time and by individual, but also a second component that is unique to each individual, but does not vary over time, and we call that alpha I. Alpha I is what we refer to as time invariant unobserved heterogeneity. Now, if alpha is not related to the other explanatory variables in our model, then alpha is like any other unobserved factor that's not systematically related to y, and it's soaked up in the error term, and we might not have to worry about it. If, however, alpha is related to other covariates in the model, then relegating alpha to the error term will be problematic, and it will result in biased estimates of our coefficients. So returning to our income example, if we believe innate ability is not related to education and our other covariates, then we can ignore alpha, and maybe we could just run a pooled OLS. If we believe that it is, this will be a problem. So Clark and Linzer 2012, which I'll provide a reference to at the end, they demonstrate what we mean by creating bias when we don't account for unobserved heterogeneity. They show this with some nice simulation models where they impose different degrees of correlation between the individual time invariant unit effects, so alpha, and the independent variables x. And in the center, B, we can see the case where there's no correlation between alpha and the independent variable x. And we can see that there'd be an unbiased estimate of beta equal to 1 in that case. In case A, we have a situation where the independent variable x is negatively correlated with the unit effect alpha, and the result is an estimated beta that's smaller than the true value of beta. And in case C, we have a situation where the independent variable is positively correlated with the unit effects, and the result is an estimated beta that's larger than the true beta. So in both A and C, we can see how the estimated coefficients would not reflect the true value of beta, so we would have biased coefficient estimates. Now, we might attempt to deal with this type of omitted variable bias through the use of instrumental variables, which we learned about in a previous lecture. However, as Kriti noted in her lecture on IVs, it's often very difficult to identify an appropriate IV. So panel data offers methods to deal with this special type of omitted variable bias, time invariant unobserved heterogeneity. Okay, so now that we've seen how this form of omitted variable bias can impact estimates of regression coefficients, we'll look at how panel data can be used to try and deal with unobserved heterogeneity, or alpha, from our previous slides. Now, there's two standard approaches to modeling variation in alpha I, the fixed effects model and the random effects model. The first approach we're going to talk about is the fixed effects model. So with the fixed effects model, we replace the unobserved error component, alpha I, with a set of fixed parameters. Here we'll call them mu1, 2, 3, all the way to mu n, one for each of the n units in our sample. So mu1 represents the net effect of unobservable factors on y that are constant over time for unit 1. And these n fixed parameters control for the net effects of all unobservable factors that differ across units but are constant over time. And this is the general idea behind fixed effects. Because fixed effects models control for all time invariant differences between individuals or units, estimated coefficients cannot be biased because of omitted time invariant characteristics. So fixed effects models are designed to study causes of change within a person or unit. And you can think of this as using each unit as a control for itself. So referring to our running example about estimating the effects of education on income from earlier, if innate ability was constant over the time period in question, then mu1 would control for that, plus all the other factors that don't change over time for individual 1. Now, there are a couple ways of operationalizing fixed effects models, and probably the most intuitive is through the least squares dummy variable estimator. And in this case, we simply create a dummy variable for each unit. For instance, if our unit of observation is an individual person, we just create a dummy variable for each person in that data set. And we then basically regress our dependent variable y on the dummy variables and then all the other explanatory variables in the model. And this gives you an idea of the intuition behind fixed effects, because we have a control variable for each unit basically that soaks up the effect of all factors unique to the individual that don't vary over time. And we can actually interpret the coefficients for these individual or unit specific dummy variables as the different intercepts for each individual or unit. And for this reason, we'll often leave out the beta naught term or the constant term. Typically though, if we have many individuals and not a lot of time periods, adding a dummy variable for each individual eats up a lot of degrees of freedom and might not be very practical. So fixed effects can also be implemented with the fixed effects estimator, and this is what's usually used. This is a way of removing time invariant factors from our model. This works by first determining the time mean of each component, which we'll call, in this case, y bar, x bar, u bar, and alpha bar. And the time mean is simply the average value of each component for the ith unit over t years. So for the panel data we showed earlier, this would be like taking income for person 1 over 3 years, over the 3 years that we observed them, say it was 2010, 2011, 2012 in our example, and just taking the average income over those 3 years. Now, you'll note that in the case of alpha I, our time invariant individual specific characteristic, the time mean is equal to the constant alpha I value because alpha I is constant and therefore the same in every time period. So we then complete what we call a within transformation, where we create a time demeaned data set. And this means that we subtract the time means, so what we calculated on our previous slide, from the actual values of YIT, XIT, UIT, and alpha I, and we run a regression on these time demeaned values. So we're running an OLS regression using the transformed data, which is now in the form of deviations from the time mean. Now, the important thing to note here is that the regression will not include any constant terms because the time mean of these factors will be the same as the actual values. So because alpha I is constant and therefore equal to alpha I bar, this nets out to 0. And the least squares dummy variable estimator and the fixed effects estimators will give you the same coefficient estimates. Though if you're using the fixed effects estimator by hand, you'd have to be careful to adjust the standard errors appropriately. Most statistical packages will do this for you anyway. You'll also note that unlike the least squares dummy variable estimator, there has to be some additional math to obtain estimates of the fixed effects parameters if you have any interest in the unit level effects on the outcome variable. We'll note here that if we were to try and run fixed effects in Stata, we could add individual dummies to our regression, like the least squares dummy variable estimator, or we could use xtreg, FE, which uses the time demeaned approach, and they should both give you the same parameter estimates. Also for Stata users, though, if you wanted to do this with dummy variables, you could use the I.dot variable function, where I.dot in our running example is the individual. And the result is that Stata creates a dummy variable, like we outlined a few slides ago, for each individual. So this would be an extended, but maybe more intuitive way to run a regression with a dummy variable for each person or a fixed effect for each person. So one of the biggest assets of the fixed effects estimator is that it generally can be used to produce unbiased coefficient estimates when the time invariant omitted factors are correlated with your explanatory variables. And this is a huge pro because the reality is that this is likely to be the case in the vast majority of the time. And this is also why you'll see fixed effects favored in the economics literature, which is often focused on modeling causal effects. But those estimates can be subject to high sample-to-sample variability when there are few observations per unit and when there's limited variability within each unit relative to the variation in Y. And what that latter point implies is that when most of the variation in our outcome variables comes from variability between subjects as opposed to within subjects, simulations have shown that fixed effects estimators don't perform well and that standard errors can be very high in some of these cases. So for example, if you are estimating the effect of a state's median income, say on crime rates, you may find that while income varies significantly across states, maybe it changes slowly over time. And in such a case, standard errors and fixed effects estimators may be large. And this can be contrasted, for instance, with, say, average opinions across states, which we'll say for this example, may vary little by state, but have substantial variation within a state. Another con of the fixed effects estimator is that if you have an interest in understanding the effect of time invariant explanatory variables, or variables that change very little over time, it won't be possible to determine their effect because these will be netted out when you time demean your data. And finally, fixed effects is optimal for estimating effects for individuals in the data set being used because the unit effects of unobserved units are unknown. So this is not necessarily the case with the random effects estimator, which we'll see in a little bit. So to demonstrate the fixed effects model in action, using an example from the literature, let's briefly take a look at Oberg et al. 2016. This is a study where the authors assessed the association between labor induction and autism spectrum disorder. In this study, we have Swedish registered data from 1992 to 2005, and the authors look at 1 million plus births and conduct a within sibling comparison. So the authors are able to control for a pretty impressive array of observable factors. It's Swedish registered data is very impressive on this front. And these things include birth year, parity, a number of maternal characteristics. What's missing here, though, is basically the unobserved factors such as environmental factors at the household level and genetic factors that are shared within families. So to try and account for these unobserved factors, the authors include controls for maternal sibling pairs, where one of the children had an induced birth and the other one did not. So there's discordance with respect to birth induction. And they use a fixed effect at the maternal sibling level to allow the underlying hazard to vary between mothers. So comparison is within siblings only. And we can see the impact that this has on our outcomes here. In the first three models, which include increasing numbers of covariates, we see a positive and significant association between labor induction and autism spectrum disorder. We see that this association is attenuated the more covariates we add. So it decreases from a hazard of 1.32 to a hazard ratio of 1.19. From the most parsimonious model, which is model 1, to the sort of kitchen sink model, which is model 3. But the effect is still significant. However, once we include the maternal sibling fixed effects, labor induction is no longer associated with ASD. And this is an indication that unobserved time invariant factors shared by maternal siblings, say maternal genetic factors or family level characteristics, may have been unaccounted for in models 1 to 3, and that this was biasing the coefficients in these models. Now, one more thing to note about fixed effects before we leave the topic is that you can include fixed effects along multiple dimensions in your model. So a common combination that you'll see is person and year fixed effects in a model. You can also have group and time fixed effects, which are components of the difference in differences model, which we talked about in a previous lecture with Jean Yoon, and where you're interacting the group and post-period fixed effects to get a treatment effect, which accounts for group level characteristics that are time invariant as well as an overall time trend. So we've seen that fixed effects will tend to produce unbiased estimates in situations where the time invariant omitted factors are correlated with regressors in our model. But what if this is not the case? What if there's reason to believe that the omitted factors are not correlated to any other independent variables in our model, or that the correlation is very low? Would we still have to run a fixed effects model, which might soak up the time invariant terms that we want to look at, or it may inflate our error term? So this is where random effects estimators come into play. If you can assume that there's no correlation between X and your unobserved heterogeneity alpha, you don't need to use a fixed effects estimator. But you can't simply run an OLS estimator or use an OLS estimator either. Because you have repeated observations for each unit, it's likely that you're going to have some serial correlation, and that's the error term at one point in time is correlated. So that time t, say, is correlated with the error term at another point in time, say s. And a quick aside on serial correlation. What this means is that the OLS estimator will not necessarily be biased, but it will be inefficient, and that standard errors can be underestimated. Basically, if we're fitting a regression line, not taking into account the fact that we had repeated observations of the same individual, the standard errors would be might be smaller than those with the true regression line. And we would be underestimating our variance here, and this can have important implications for hypothesis testing, leading us possibly to conclude that a covariate is significant when it really isn't. So instead, you could use a technique that is more efficient than fixed effects and doesn't eat up so many degrees of freedom, but that, unlike pooled OLS, still accounts for unobserved heterogeneity in our model. And with fixed effects, we simply got rid of the alpha term through a within transformation. That is by time demeaning our data. With pooled OLS, we simply ignore alpha I and we let it get subsumed by the error term. Random effects is a compromise between these two models, and it maximizes efficiency by calculating beta as a weighted average of the fixed effects estimator and the pooled OLS estimator. So there's a bit of Greek here, but I just want to show the two components that come into play when a random effects estimator is used, and how we transform the fixed effects system to make it more efficient. So random effects essentially transforms the fixed effects system with an inverse variance weight. We'll call that lambda, where lambda is 1 minus the square root of the variance of our UIT, our idiosyncratic error, over the variance of UIT plus t times the variance of alpha I, our unit effects. And we use lambda to what they call quasi-time demean the data, the system. This is like taking off a fraction of the time demeaned values instead of the full time demeaned values as we would with fixed effects. So let's get rid of some of the equations and just talk a bit about the intuition behind random effects. Lambda is typically between 0 and 1. When lambda is equal to 0, the system is equal to a pooled OLS regression. And this makes sense because in order for lambda to be 0, sigma alpha, so the variation in our unobserved heterogeneity term, would have to be 0. And this means that variation in alpha does not comprise a significant portion of the error term, and we can simply ignore it, maybe. Meanwhile, when the variance of alpha is very large, then lambda will equal 1, and the random effects estimator is equal to the fixed effects estimator. And this makes sense, since alpha would then comprise a significant portion of the error term, and it can't simply be ignored. So the random effects estimator would try to remove as much of this effect as possible, much like the fixed effects estimator does. Essentially what happens is that groups with outlying unit effects will have their alpha I shrunk back towards the mean alpha, which brings the estimated beta closer to the pooled OLS estimate and further from the fixed effects estimate. And the effect is going to be greatest for units containing fewer observations and when estimates of the variance of alpha I are close to 0. So to get an idea of what's going on when we use the random effects estimator in a statistical package, let's break down what's happening. The random effects and the statistical package I'm talking about here is Stata. The random effects estimator is operationalized in 2 stages. First, we obtain an estimate of lambda or lambda hat by determining the variance of U, IT, and alpha. And these estimates are usually obtained by estimating a fixed effects or OLS regression. You then substitute lambda hat for lambda in our transform system, which is what we referred to in an earlier slide as quasi-demeaning our data. And then you just run OLS on the transformed data. So in Stata, we can do this using the xtreg, RE command. Now, there are a lot of important advantages for random effects models. First, as we noted, estimates of beta will have less variance because outlying unit effects will have their alpha shrunk back down to the mean alpha. And this brings beta closer to the pooled OLS estimate and leads to estimates that are closer on average to the true value in any particular sample. So a lot of researchers may favor random effects because some argue that the inferences from random effects are more generalizable beyond the sample in a given analysis. Another major advantage is that we can include time invariant covariates in the model, and that's a big one. With fixed effects, these are washed away by the estimator, which is a disadvantage if we want to know what the effect of that variable is on our outcome. A third advantage is that random effects can be used when we have small samples within units, so which for fixed effects models can result in large variation or even an inability to estimate the model. So what are the cons? The main reason economists and others interested in causal inference do not favor random effects is because it almost inevitably breaks the assumption that there's no correlation between alpha I and other covariates. And this will introduce bias in estimating beta. And the greater the correlation between covariates in the model and alpha I, the greater the bias in the estimates of beta. Finally, a con may be that we don't actually estimate alpha I in random effects models, and that might be of interest to some researchers as well. So I just want to recap briefly with a poll. I'd like to ask a quick question. From an econometric standpoint, when is it appropriate to use random effects instead of fixed effects?
Okay, so that poll is now open. Your choices are A, when the unobserved unit-specific factors are not correlated with the covariates in the model. There's B, when the unobserved unit-specific factors are correlated with the covariates in the model. And there's C, the models can be used interchangeably. So we have the responses coming in, and once it slows down, I will go ahead and close that poll. And it's still coming in pretty rapidly. So I'm going to go ahead and close that poll right now. And we have 59% said A, 27% say B, and 2% say C. And back to you.
Great. Great. So yeah, from the correct answer from an econometric standpoint, in theory at least, is what most of the people responded with. It's the first one. So when unobserved, unit-specific factors, alpha I, are not correlated with the covariates in the model. And this is the key assumption in econometrics that distinguishes the use of the two models. Now, we're going to see in a bit, though, that this is not necessarily a hard and fast rule in applied research. One thing I'd like to touch on before discussing choosing between the two models is clustered data. We've considered fixed effects and random effects in the context of panel data, which was observing the same units over time. Another way to apply fixed random effects is when we have clustered data, when observations are clustered into groups. For instance, health facilities in a geographic region, patients in a hospital, individuals in a family, or with a certain health status. The intuition here is similar to panel data. If we believe unobserved common group level characteristics can affect our outcomes, and we don't account for these factors, we can have biased estimates due to unobserved heterogeneity at the group level. So in place of our I individual or unit and T time subscripts, we would instead have subscripts in our equations for the group and observation identification within each group. So Dielman and Templin, which I provide a reference to at the end, provide a very nice overview of how the same intuition we've described so far up to this point can be applied to clustered data. To determine which model to use, the Hausman test is often used. This is a measure of the difference between fixed effects estimates of the beta coefficient and random effects estimates of the beta coefficient. So the null hypothesis here is that the coefficients estimated by the random effects estimator are the same as the ones estimated by the fixed effects estimator. And we're testing whether the covariance between our unobserved heterogeneity term, alpha I, and covariates x are equal to 0. If this were the case, then we would use the random effects estimator. And a rejection of the null then indicates that the two models are different and we should reject random effects in favor of fixed effects. As widely used as it is, there are some drawbacks to the Hausman test. So Clark and Linzer 2012, which I provide a reference to later, use simulations to demonstrate a number of scenarios where the Hausman test can lead to erroneous conclusions. And they note that a rejection of the null hypothesis may not necessarily be due to covariance between alpha I and covariates in the model. Could also be due to because the test does not have sufficient statistical power to detect departures from the null. Because of this potential, they note that careful consideration should go into the choice of estimator. There's always a trade-off between bias reduction and variance reduction, and the Hausman test doesn't necessarily help in evaluating this trade-off, and I'm going to elaborate on this in a few slides. First, though, I wanted to turn to Twitter, of all places, for a few seconds. Recently, Todd Wagner and Libby Disney-Greer from HERC brought Jeffrey Wooldridge's Twitter account to my attention, and I'd actually suggest checking this out periodically for both helpful econometric hints as well as really cute cat pictures. Last month, he addressed a common way that the Hausman test is used inappropriately, in addition to highlighting the econometric standpoint that there are few scenarios where fixed effects are preferable to random effects. So relevant to what we're covering now, though, he did highlight that the most common way that the Hausman test is operationalized doesn't take into account serial correlation and heteroscedasticity. So he suggests either adjusting the traditional Hausman test or else using correlated random effects to test for differences between the two. And briefly, the correlated random effects approach would involve computing the panel level average of time varying components. Then you would use a random effects estimator to regress covariates and panel level means against the outcome variable. And you would be able, in this case, to use a robust variance covariance matrix that accounts for serial correlation and heteroscedasticity. So taking care of that concern that Jeffrey Wooldridge's Twitter brought up, and then testing whether the panel level means variables are jointly zero. So a rejection of the null here suggests that there's correlation between the time invariant unobservables and your regressions. So the fixed effects assumptions are satisfied. So for Stata code on how to operationalize this, you can check out the PINs in 2015 reference on the references slide in this presentation. Now, Clark and Linzer have also come up with some useful tips that they outline for choosing between fixed and random effects. They suggest 3 considerations when choosing. First is the extent to which variation in the explanatory variable is primarily within unit as opposed to across units. They warn about the quote unquote sluggish case where independent variables change very gradually over time relative to changes in the dependent variable. So in cases where this happens, correlation between the unit fixed effects and those sluggish variables can actually destabilize estimates. The second factor to consider is the amount of data that one has, so the number of units and observations per unit. So when a data set contains many units or is organized according to a complex data structure where observations are grouped into more than one unit or at more than 2 levels, the authors there argue that random effects models can be less complicated to specify and interpret. Third, you have to consider the goal of the modeling exercise. So with fixed effects, out of sample predictions aren't possible because the unit effects for unobserved units are unknown. With random effects, we can estimate the distribution of the unit effect, including the mean effect, theoretically in the broader underlying population. So even if the observed units are fixed, this may be a reason to choose random effects over fixed effects. So Clark and Linzer actually provide a nice rubric for how to decide between the 2 models that can serve as a guide to researchers. They base this advice on evidence from simulation models. So when there's variation in X, primarily within units, they find that there's rarely any difference between fixed effects and random effects estimators. So you'll recall an example of predominantly within unit variation that we talked about was average opinions across state, where the average opinion in each state might be similar, but individual opinions within the state vary a lot. So in these cases, only when there's little data and correlation between the regressor and the unit effects is exceptionally high. So when that correlation is very high, so in their simulations, there are correlations of 0.9. Only then did the fixed effects estimator outperform the random effects in their simulations. So in this specific case, they find that any bias in the slope parameter estimate is compensated for by the increase in efficiency. So ultimately, they advise in this case that researchers should use whichever model better serves the purposes of the research. If you want to make predictions about unobserved units, and you're not concerned about collinearity between the regressor and random and unit effects, then random effects estimators could be used because a fixed effects estimator could not make these predictions. It's not so straightforward when there's variation primarily across units. So an example of this you'll recall was when we think about changes in median income within states over time. Over time, median income will change slowly. So most of the variation in the dependent variable will be explained by differences in, say, wealth across states. So in these situations, the choice of estimator depends on the amount of data and the underlying level of correlation between the unit effects and the regressors. So in that scenario, random effects may be preferred when there are few observations per unit and few units. When there are either few observations per unit or few units, random effects only preferred if the correlation between alpha and the other covariates is low. Otherwise, fixed effects is preferred. Finally, if there are many observations per unit and many units, fixed effects is preferred, unless the correlation between alpha and the covariates is close to zero. So often very case specific. So we've mapped out some more detailed advice on choosing between fixed effects and random effects, but actually these criteria are really not commonly applied in the literature. A lot of the time, the choice of fixed effects or random effects will come down to the method most favored by a discipline. So in a review of health, economic, and poli-sci literature, Dielman and Templin show that while health sciences tend to favor random effects, economics and political science researchers tend to most often employ fixed effects models. Some of this comes down to the fact that health sciences researchers may be working in the framework of an RCT, in which unobserved effects are truly uncorrelated with the variable indicating treatment. Economists, meanwhile, most often work with observational data and are often most interested in causal inference as opposed to prediction. So I'll conclude by noting that some of these differences may also come down to differences in terminology. So Gelman, which I have referenced on the next slide, provides a nice overview of some of the different ways that fixed effects and random effects are defined. In some cases, the terms are applied to different concepts. So it can be very confusing when you're in an interdisciplinary context to figure out what a researcher is referring to. One thing in particular is that in some contexts, the fixed effect is the population averaged effect and random effects is the subject-specific effect. The best advice I can give here is just asking people to clarify what they mean when they use these terms, because it's very easy to talk past someone assuming you're both referring to the same model. And I just want to point out some references that were used to put this together, and that could be useful resources. For those who want some more detail about how to think about what we've just discussed in the context of clustered instead of panel data, Dielman and Templin, as I mentioned before, provides a very accessible overview of this. It's similar to the Clark and Linzer paper, and they run a number of simulation models to demonstrate when fixed effects versus random effects may be most appropriate with clustered data. And finally, before jumping to any questions that might have come up, I just want to give a shout out to Mark Winkevant, who will be giving our next lecture, HERC lecture, and the topic will be costs as the dependent variable, and that will be next Wednesday, April 14th. And that's it. If there's any questions.
Hi, Dave. This is Laura.
Hey.
Awesome presentation.
Thanks.
Super informative. We've got a couple of questions that came up during, and then there's some that are popping up right now.
Okay.
So the first one is actually, I think it'll be a pretty quick one for you to answer, but since I'm not a stated guru, I had no clue how to answer it. But so in your fixed effects section of the lecture, you talked about XTREC. And the question is, is the dummy variable approach and XP-RAG approach the same?
Mm.
Yes, so I think it's by default. How do you use XP-RAG with that dummy variable approach?
Okay, yeah, so that's a great question. And they should give you the same parameter estimates, and with maybe some differences in the variance. So it sort of depends if there's sort of multiple levels of fixed effects that you want to include. Sometimes for larger groups, I might opt for the I dot variable approach. But if it's sort of at the individual level and there are many units of observation, you might opt for the fixed effects approach. Hope that answers it.
Hey, the other question that popped up is, and this was something that I answered, but it was more so from my epi mindset. And so I wanted to get, I wanted to use the econometrics approach on this. So the question is there a rule of thumb for how big the sample should be to avoid low statistical power? What I had always heard was, number of observations should be equal to your number of variables times 10. So I'm wondering kind of what you use. Yeah.
Oh, that's great. I didn't have a rule of thumb actually. So I was actually very excited that you were going to be the backup for this presentation because you provide that epi view. And I know, like, based on that last slide, how different they can be. I don't have a rule of thumb, so I'm glad you brought that up. Yeah, that's great.
Awesome. Yay. So now we're getting into some of the ones that popped up right towards the end. And one of them has to do with, you listed the status or reference for data code for the Munlach approach. Are you aware of any SAS code approaches to use it?
I'm not, but what I would recommend if you're interested is checking out the I think it's the Dielman and Templin one, because they tell you what the intuition there is. And so it's actually fairly easy to implement that approach, by just including those mean values in your regression. And so if there's just a few paragraphs that explain the intuition in that article, so it's the Dielman and Templin 2014. I'd recommend checking that out. I don't know what the code would look like, but the intuition there should be fairly easy to implement.
Awesome. Yay. And just kind of rolling down the list here. So one of the other questions that came up that was really interesting that I think will be a fun one to talk about is, how do you test the assumption that alpha is not correlated with X?
Right. And you can actually look at the, and actually I can tell you the Clark and Linzer paper talk a little bit about this, looking at the correlation between the time means, so the mean over time for individual X, for variable X. But do you have any recommendations on that front? Any specific tests from the epi literature?
No, that pretty much, yeah, that was kind of, that was the way I was thinking too. So it's nice to know that the Clark and Linzer article has like a lot of descriptives on it, or a little bit more of a description.
And I actually want to circle back to other question that came up earlier, that the rules of thumb. So they go through all these simulation models, and I don't know if I'd call them rules of thumb, but they do come up with some nice, I guess you could call them that, but just that to do with sample size and those sorts of things. So I would recommend having a look at the Clark and Linzer paper for that. They're not anything I have actually ever used, so that's why, like I said, I was glad you brought up that epi rule of thumb. But they do talk about it and the results of their simulations and what they think might be appropriate.
Awesome. The next question on here is, so if the data are clustered, which model is more appropriate? And I think that's referring to the difference between panel and clustered data and whether or not you should use a fixed effects or random effects. I don't know if you want to like, it sounds like it's that's kind of like summarizing that that awesome slide that you presented that kind of gave you an idea of like, if this is what's going on, then you should go with a fixed effects model. Is that a good summary of how to choose?
I would say so. I would say, yeah, so they provide this and so actually, I'll go back to the references slide, because what's nice is that Dielman and Templin actually do almost the same thing that Clark and Linzer do, but they do it for clustered data. So to the extent that Clark and Linzer have these sort of rules of thumb based on, panel data, you can check out Dielman and Templin for their rules of thumb based on their set of simulations, which was for clustered data. I think they're quite similar, but yeah, I think if you're interested primarily in clustered data, that's the one I would look at.
Awesome. So Nick asked, he wanted to clarify the definition of fixed and random effects, kind of understanding the difference, just the difference between those two and your interpretation of how they differ.
Okay.
Outside of, I think, a model standpoint. So, I don't know, I always think of it more so like it's almost like a dummy variable as opposed to like the random effect. How it's included in a model is very different.
Yeah, it's a lot of slides that went, that it is complicated. I think the intuition for me is exactly when I think about fixed effect, I think about the dummy variable estimator, and basically like just sticking a dummy variable in there for every individual. When I think about random effects, I think about a lot of those complicated equations that I showed earlier with the sort of weighting between the two, but I think of it as sort of like a compromise between the fixed effect and the pooled OLS estimator. I don't know if that answers the question, but that's how I think of the intuition between the two of them. I don't know.
Nice. And that also leads into one of the other questions that was asked was when you think about mixed effects models, and can those be used to resolve some of these issues of choosing between a fixed effect and a random effect?
Yeah, that's a great question. So what I just want to, and then again, I don't want to make sure I'm thinking about the same type of model when we say mixed effects, but there's a sort of within between estimator. Is that, I hope maybe that's what they're talking about. But that's actually somewhat related to the Mundlack slide that I showed earlier. Or basically, if you go to this Pinson reference, then that's kind of what they're getting at there. If that's the estimator that we're talking about, the same one, where it kind of very, as the person points out, sort of some think that it's sort of the best of both worlds. And again, I can emphasize that Dielman and Templin provide a very nice intuitive description, and their simulations actually look at fixed effects, random effects, and then that what they call the within between estimator. And actually they find that that's the one that performs the best in a lot of the scenarios. So good job to whoever made that comment. That's sort of what the simulations have found for that particular paper.
And we have one final question that really does play off of that and the standard errors of that, of some along those lines. So the question is, how do clustered standard errors relate to fixed effects models? So the clarifying on this question, the author says, I've read that clustered standard errors are used to account for within group correlation, while fixed effects can be between group variation. Is there another more important way to distinguish between the clustered standard errors as opposed to or in combination with fixed effects for cluster data? And I think that, I mean, like you said, it's the within group correlation, between group correlation is usually the easiest way to distinguish between those two. Is that your thoughts as well, Jo?
I would say so, yeah. Yeah, I think that actually plays quite nicely into their discussion of the, exactly that, of the within between estimator, yeah.
Yeah, awesome. Well, we are at the top of the hour. Maria?
Yeah, I just want to, do you have any closing remarks before I close everything out?
Just thank you so much for everyone's time. Thank you so much, Laura and Maria. And yeah, check out Mark Kuntavang's cost as the dependent variable lecture in a week's time.